Hello everyone and welcome to another AP Computer Science video. Today's video we're going to start a new topic, and this is the second topic that really kind of changes the level of complexity that we can produce in our programs. The first one we saw was conditional statements, the ability to make decisions based on input, based on comparisons, based on all kinds of different things, and that was a pretty big deal to change the flow of a program. That's a big step forward. And so the topic we're going to discuss today, that of iteration, is another topic where we will have a lot of control over a program. And now, really, we've kind of thrown the idea of a program being linear out the window. It's more like kind of a roller coaster where it might go down a straight path, but it might loop on itself and repeat itself. Or if we're going through a maze, the idea that we might repeat certain sections of code. That's a very important idea, and it's a very powerful one. It allows us to minimize how much code we have to write and not make as many assumptions as we might have initially done. So for example, assuming that a user is going to type in exactly 3 things, that's not unreasonable to do, but potentially a more flexible program could let the user type in as many things as they want. Or making the assumption that they're not going to make a mistake in inputting something and just letting it and moving on if we can, and letting the program crash otherwise. That's something that we can now potentially avoid with the ability to re-ask a question or revalidate some input or check things in a way that allows us to kind of get stuck and repeat ourselves. So this is a pretty big step. So we're going to make a new package in our code, in our notes, that's going to hold a bunch of different examples that we're going to be doing. So I'm going to right-click on my project. I'm going to say New in a Java package. So our previous package was called Control Structures. We're going to do our package is going to be called Iteration. So iteration, if you don't know what the word iterate means, to iterate is to repeat or do again and again, right? To iterate, or is to actually maybe go through several things, to do multiple things. But typically iteration means that you're going to repeat yourself. So that's the idea that we're going to have here. So I'll draw a diagram in a moment when we talk about this, but I'm going to go ahead and make a new class first. So let's make a new Java class. I'm going to call it while loops, because this is the first thing we're going to discuss is while loops and what is a while loop and this idea of iteration. So here's our class. Let's go ahead and make a main to start with. I use my shortcut, and there it is. So let's put some notes real quick. Essentially, again, iteration is the ability to repeat ourselves, and so we'll say we can use iteration, or we often call them loops. And the idea of a loop is basically a section of code that loops or repeats itself, and that's a pretty important idea. And so often we'll hear this term while loop, for loop, do while loop. There's many different loops, and it literally is because of if we draw the diagram, we can see kind of a repetition or a loop in our drawing. Right, so the idea is that we can use loops to repeatedly ask questions, and we'll see how while loops are very similar, and in general loops are very similar to if statements, except that instead of moving along after the answer has been determined, like an if statement does or an if else does, we'll see that we can actually go back and repeat the question again and again until some condition is satisfied or not satisfied. Right, so we'll see that idea. So we're going to say the first type of loop we're going to discuss is a while loop. A Boolean condition is evaluated first, and if true, body of code is run, and once completed, the condition is evaluated again. So the idea is that we'll ask a question. If it's true, we'll run some code, and then we'll go back to the question, and we'll repeat this. And potentially this could run many, many times. So let's draw a diagram to represent what this would look like. So I'm going to go ahead and pull up my whiteboard, and we'll see how we can potentially draw this picture. So let's give it a moment to open up. It's kind of slow. Here we go. Oh, so that's from before. Let's go ahead and clear it out. Clear canvas. And so our drawing is going to be very similar to an if statement, but we're going to start off at the top, and we'll start. There's our program flow, and we'll do the same kind of idea where we ask a question and we represent a question in our diagram as a diamond, and there's essentially a Boolean a Boolean expression that is either true or false. And so what we'll do is we'll go ahead and say there's two paths that we can take, and I'm going to draw this, and we'll see how this is kind of different, and we'll say this is code segment A, and we'll come back here. And so what we're going to do is our program begins going this way. It can only come this way. It's going down. We ask our question. If our answer is true, then we run into code block A, and then we come back and loop around to the question again. And so you can see now we have this kind of looping pattern, and this is where we could potentially get trapped, either on purpose or potentially as a mistake. But the idea is that we can repeat this question and code block A again and again. Now, what's nice is the fact is that in code block A, we may be using variables that might change. So theoretically, if we're going to do this correctly, the idea is that eventually something that we do in our body should make it so that the question eventually becomes false. And so here's the path when the question is false. So at some point, whether it's 1 time or 700 times or 4,000 times or any number of times, even 0 times potentially, eventually the question will no longer give us a true result, and then we will see our program will continue and move on to whatever the next segment might be. And again, within this code block A could be any other code. And so the idea is that we're going to be using curly braces just like an if statement to do the same thing. But now the idea is basically this is kind of an if statement that is asked again and again and again. And we call this a while loop because we're saying while this condition is true, run some code and then ask again. So while this is true, run and ask again, run and ask again and again and again. Eventually we're going to say, oh, it's false, and let's exit. Right? So typically the question we ask, if it's true, we want if we want to run a particular code, then it should be true. If we want to skip this code, then it could be false. So I hope that it's clear from the diagram that it's possible to never do this loop at all. The question could be false immediately, and then we would just go in a straight line as if the loop were not there. And only when it is true. So it is also conditional, but the idea is that this condition could potentially stay true and continue to force us to repeat section A over and over again. So given this, let's go ahead and try to do an example. And our first example will be very, very simple. But let's go ahead and write the layout or the format of our while loop. The format of our while loop is going to be the keyword while, just like the if statement, a set of parentheses, and then a Boolean expression within our parentheses, and then our body of code, which could be doing potentially anything. And again, generally speaking, we should be setting up either variables or some system that allows the loop to eventually become false. And if we don't, then we have two possibilities. The loop will never run, or to run forever. And we can imagine a program that runs forever in a particular section could be a problem. In fact, we've all probably experienced a program kind of hanging and just sitting and waiting and looping, and then eventually maybe your Windows will say, oh, the program is not responding. And so potentially it could be that there are flaws or bugs in code which cause loops to never end. Now, when it comes to that kind of thing, it might be way more complex depending on the system or the program, but generally speaking, it's possible for a semantic bug that we as programmers might write to kind of trap us in a loop and then never leave. And that's basically a program is stuck, and that's a huge problem. So we do have to be very careful. With the power comes the great responsibility of managing our code to not get stuck in infinite loops. We'll call infinite loops because theoretically, if you had the computer running forever, the program would run forever. It would never get out of the loop. So that's our general layout. Let's go ahead and try an example. We're going to print the numbers from 1 to 10. So we're going to say print the numbers 1 to 10 inclusive. So our setup has to be in a way that it's going to ask a question that tells us, should we continue repeating ourselves or not? And eventually we should get a no, and that's when the loop will end. So in this example, we're going to have what we often call either a counter or a manager or a kind of control variable that controls whether the loop is going to repeat itself or stop. And so often you'll hear a counter because we're just counting, and usually the variable does nothing more than keep the loop either running or not. But it could have other meaning. In our example, it's going to both control the repetition and be the value that we want to print. So let's go ahead and make a variable. We're going to print the whole numbers from 1 to 10. Obviously, we can't do real numbers because there's an infinite number of real numbers between the numbers 1 and 10. So we're going to do integer values. So let's start off by making an integer variable, and we'll call it num, and we'll initialize it to 1 because that's the first number we want to print. And so now we have to write our while loop. So the keyword while, and then our parentheses, and I'm going to go ahead and quickly put our curly braces just so that's a little bit more done. And now if the error occurs, it's going to say, well, you need, it says illegal sort of expression saying you need to put something Boolean here. Whatever it is, as simple or as complex as it is, it must be a Boolean expression. It must evaluate to true or false. It could just be a simple comparison of numbers. It could be a bunch of ands, ors, and nots mixed together. It could be based on sensors. It could be based on user input. There's kind of no limit to where it comes from, just like if statements. But at the end of the day, the key is that it's either true or false. So in this example, what tells us that we should continue? The question we ask when we implement or fill in the Boolean expression is, what must be true for us to do the body of the code? So sometimes it's easy or easier to write the condition after we've written the body. If we know what we want to do, that can give us a clue as to when we should be allowed to do it. And so in this example, what I want to do is print out the numbers 1 to 10. Well, num contains a number and it starts at 1, so maybe our body is as simple as printing whatever's inside of num. So let's try doing that. So we'll say system.out, and ours is going to show up one after the other, not going to be in one line. We'll start off very simple, and we'll start off with just each number on a separate line. And so I can just print the value num. So it's going to print 1. So what should be true for us to continue printing? Now, first of all, do we only want to print the number 1? We don't want to say 1, 1, 1, 1, 1. We want to potentially say 1, 2, 3, and so on. And so the printing of the number is not enough. We should maybe increase the number. So num starts at 1. We display the 1. Then maybe we should increase it to a 2 and then display the 2. And then we'll increase it to a 3 and display the 3. And eventually, at some point, we'll stop. And that's what's going to tell us when our condition, what should be true of our condition for us to continue, and theoretically what should be false that would stop it. So to increase num, we have several choices. I'm going to write all 3 just so we have a sense of it, and then we'll talk about why 1 is more common. And we kind of already seen it, but this is kind of more of a proof. We'll say num is equal to num plus 1. So what are we saying here? We're saying take whatever value it used to be, add 1 to it, and now remember it as the new value. A second way of writing this could have been num plus equal 1. We saw that that was a compound assignment operator that adds 1 to the variable and then reassigns it immediately. So it's the same thing. And the last version we saw was the increment operator. If you're going to increase by 1, then we can use the plus plus operator or increment operator to do so. And so we'll see that very shortly, loops tend to use increment operators and decrement operators more than anything, mainly because often we want to iterate one number at a time or do one increase at a time. We could do plus equal 2, plus equal 4, and so we'll do some examples of different things, but the idea is that the change, something should change, and this is another hint as to what our condition should be. If we're printing out the content of num and we're updating num, then it's a very real possibility that the condition must be reliant on this variable that changes, right? A variable is a value that changes. So the fact that it might be true based on num at some point, and maybe it'll eventually be false. So what should our condition be? If I want to print the numbers 1 to 10, I print 1, it increases to 2. I print 2, it increases to 3. I print 3, it increases to 4, and so on. When do we no longer care to print it? At 10. If it was 10, we would print 10, and then we'd go to 11. At 11, would we want to print it? The answer would be no. So ideally, this loop should not run this body if num is 11. If it starts at 1, then we can say, well, what should be true for us to continue to print and repeatedly print as long as num is less than 11. Once it's equal to 11 or greater, we should no longer print. So our condition is going to be while num is less than 11. Now that's one possibility. We're going to write it again in a moment, and we'll see that there's actually a variety of ways to write this, and there's kind of no limit, but this is one possibility. So let's go ahead and see what happens. I'm going to run it. We'll see in a moment the output will come out, and we can see hopefully if we did it correctly, and there it is. And if I scroll up, there was the first one, there was the second one, and you see that I did not print all these manually. I literally have one print in one increment, and it prints all of them. The question is asked, is 1 less than 11? It is, so we print 1. 1 plus 1 is 2, we remember 2. We come back to the top. Is 2 less than 11? Yes, so we print 2, 2 becomes 3. Is 3 less than 11? Yes, and we print 3 and we go up, and eventually we get to 10. Is 10 less than 11? Yes, we print 10, we increase it to 11, we come back. Is 11 less than 11? That is a false statement. 11 is not strictly less than 11, it is equal to, and therefore our loop ends, we skip past the body, and we move on to whatever our thing is. So I'm going to go ahead and print out a message. We'll print something like finish. And let's run it again, and we should see that the finish print should happen once we get to the 10. The 11 does not occur because 11 is not strictly less than 11. How else could we write this? The condition could have been adjusted. We know that it should be true if it's including 10, so we could have potentially written, instead of strictly less than 11, we could have said less than or equal to 10. Let me run it again. Let's see if we get the same result. 1 to 10, no 11. Because again, if num is 1, 1 is less than or equal to 10. We print it, we increase. 2 is less than or equal to 10. We print it, we increase. Eventually we get to 9. Is 9 less than or equal to 10? Yes, we print it, we increase to 10. Is 10 less than or equal to 10? The answer is true, it is. So we print 10, it becomes 11. Is 11 less than or equal to 10? The answer is no. So the loop ends, we jump past the body, we do not run it again, and we print our finish. And there's our output, 1 through 10, printed. So let's do this again. But let's reset num to be equal to 1, because at the end, because num, so if we printed out what the value of num would be, actually let's do that real quick. Hopefully we see that because num was declared above the while loop in the scope of the main, it exists for all of main, so that means we can refer to it on line 31, and we should ask ourselves, what value does it contain? And the answer should be 11, because that's what caused the loop to stop. So if we print out num and we attach it, we should see the number 11, because that's what caused the condition to be false, and there it is. Right? So if we're going to use it again, let's reset num to equal to 1 so we can make another loop. So why don't we print and we'll get a little more complex now, why don't we print the numbers from 1 to 10 that are odd? Only if the number's odd. So 1, 3, 5, 7, 9. So how would we do this? Our while loop would be while, there's our keyword, our parentheses, our condition I'm going to leave blank temporarily, our body. And again, sometimes our body kind of gives us information about the condition. And I'll say that in here, it's not, in this example, it's not important. We can do either one. And there's more than one way to do it, but we're going to do it simply as a loop. You may think about it momentarily and say, oh, I could ask the question, is the number even or odd? And if it's even, do nothing, and if it's odd, print it. But we don't have to even ask a question. We can simply do our arithmetic in a slightly different way. So let's print out our number. And we're going to make the assumption that if we're printing it, it must be odd. And so we're going to print out num. And now here's the thing. If num starts as 1, and I want to go to the next odd number, what am I going to add to it? If I add 1, it becomes 2, so that can't be. If I add 2, it becomes 3, which is the next odd number. And if I'm at 3 and I add 2, what do I get? 5, the next odd number. So if you start at an odd number, like 1, and you add 2, you will always be on an odd number. So this is what we're going to do. Instead of increasing by 1, we're going to increase by 2. So now I'm not allowed to use num++ because that would only go by 1. I could maybe call it twice, but then that's kind of silly, so why don't we just say num plus equals 2, or num equals num plus 2. Either one of those is an acceptable choice. I use the shorter one just because I prefer to do as little typing as possible. And then now my condition, if I'm making the assumption that it's odd, and I'm guaranteeing it's odd by starting odd and going by 2s, then the condition is the same condition. So while num, and again I can do less than 11 or less than or equal to 10. And let's go ahead and print out the same exact thing afterwards. And I'll put finish 2 just so we know that it's the second one. So here we go. Let's run it again. And so there's the 1 through 10, the original loop that goes all through 10. There's our finish in num 11. 1, 3, 5, 7, 9. And then we finish, and then 11. Again, why? Because is 1 less than or equal to 10? Yes, we print out 1. 1 plus 2 is 3. 3 is remembered. Is 3 less than 10? Yes. So then now 3 plus 2 is 5. 5 less than 10, and so on. So the result is every odd number between 1 and 10, including 1. And 10 would have been included, but it's not. It is not odd. It's even, so that's why it doesn't show up. So let's try something a little more challenging. Why don't we do the odd numbers between 1 and 100, but going backwards. So if we start at 100, then we're going to, or if we're going to start at, well, we can start wherever we want, but I want to go backwards. So I would say 99, 97. Actually, let's do even numbers. The even numbers starting at 100. So 100, 98, 96, 94, 93, 92, and so on, up to the number 1. So from 1 to 100, even numbers, but going from large to small. So where do we start? We're going to start at the number 100. Since we're going backwards, we might as well begin with num equal to 100. That's our upper bound. And so this time we're kind of the same concept, but our condition is just going to be kind of flipped because we're going downwards. So instead of adding, we may be subtracting. This is where it becomes very arbitrary, and it's really just a matter of what you think works best. So let's go ahead and try saying while in our body. And this time I'm going to do the condition. And first, just because I think that we're hopefully seeing the kind of pattern, what should be true for us to continue to print? If we're the number 100, we're going to print. If we're the number 98, we're going to print. At some point, we should stop printing. But our question is a positive question. What should be true for us to continue printing? Well, the number should be greater than 1. Or equal to 1, right? Because we want to include 1 potentially, even though we know it's not going to just because it's an even numbers, but the idea is that we're including 1 just like we included in the first one. So we could say while num is greater than or equal to 1. Because, again, we want to include 1, and we're starting large and going smaller. So now what is our body? We're going to print out the number just like we did before. So we'll print out num. And we will now, we start on an even number, and we want to go down to only evens, so the same will apply, but instead of doing plus equals 2, we will say minus equals, because we're going downward. If we did plus equals 2, potentially this would never end, because if you start at 100, is 100 greater than 1? Yes. And then we print the number 100, and then we add, we'd go to 102. It's going to be greater than 100. It's going to actually keep going, and it potentially, theoretically, it would run forever. The real answer is it won't run forever. It'll run until we run out of integers to use on the positive end, so around 2 billion, and then it'll actually cause what's called an overflow error, which will mean that the number will go from a very positive number to a very negative, and then it'll stop, which will be very strange. But it'll take a while because it's going to print every single even number between, it would print from 100 to 2 billion. So we don't want to do that. We want to make sure we subtract to go downward so it ends where we expect it to. And then let's go ahead and print out our finish and our num to validate that this is the case. We'll put finish 3. And now before I run, ask yourself, what do we expect num to be after the loop is over? If the condition was false, what would have made it so? So let's go ahead and run it and think about that, and we can check your answer. And there it is. If I scroll up, there was the finish 2. There it was, 100, 98, 96, 94, and so on. Those are all even numbers. And eventually we get to finish 3, and num is 0, because if it wasn't 0, if it was bigger or equal to 1, we would have continued looping. It had to have been 0 to stop. So there it is. A loop that goes backwards. And now from this, we can kind of go crazy and do any number of things. If I asked you to print the numbers between 1 and 100 that are multiples of 5, then what would we do? If we start at the number 1, I mean, we could start at the number 1 and ask a question, or we could do, and I'll do that right now just because, or if we had the ability to choose where we start, we might start on the number 5 and then go up by 5 each time. So we don't have to use if statements, really, we don't want to, but I'm going to now, mainly because I want to show you that nesting, the idea of putting conditional statements or loops inside of other conditional statements or loops, is a perfectly reasonable thing to do. And so asking a question within a loop repeatedly is a very powerful technique. And I do want to point out that this is really powerful because I can arbitrarily make it from 1,000 to 1 in even numbers. And now notice that it was very quick. It's still, my computer is very fast, and a program that takes to print 1,000 numbers is 0 seconds. It's basically instantaneous. But the idea is that that's every even number from 1,000 to 1. Right? So there it is. 1,998 and so on. And so we can kind of, this is what makes a loop very powerful, because it will repeat dynamically based on your condition. It's not a set or known thing. It's known maybe because of the logic, but the reality is that it could be even more dynamic if we use user input, if we let them type in the number they want to start at. So one human might type in the number 1,000, one human might type in the number 40 million. And so that would give us our program a very flexible power, and that's a big deal. So let's do that one last example. Let's print out the numbers from 1 to 100 in the small to big, but only multiples of 6. So, but we're going to start at 1. We're going to force ourselves to start at 1. And this may not be the most efficient loop, and I'll say that efficiency is something that initially we don't worry about so much, but as we learn more skills and more tools, we do have to be careful, because even though loops are powerful, they can be expensive. Running 1,000 times may seem instantaneous here, but if we ran 1,000,000 times, is it the same speed? Is it fast? Is it slow? And depending on what you do in the loop, it could be faster or slower. So we have to be very aware of our efficiency as we go along. For now, it's not a big deal. And running through numbers, even if it's 1,000,000 numbers, that's a very easy thing if we're going up by 1 each time. It's super quick and fast for most computers, modern computers. In the past, what really drove computer science and the research is, can we make this more efficient? Because if you think about it, in the 1960s, a hard drive of 80 megabytes might have been the size of a first floor in an entire building. And now we carry thumb drives with hundreds of gigabytes, or USBs with hundreds of gigabytes, laptops with terabytes worth of data. And so efficiency of looping through information and our programs was much more important in the past. It's still very important for the kind of work that we do now, but we're a little more or a little less worried at this point for at least our beginning learning. So let's do this. We're going to start num at 1 again, and we're going to make our while loop. I'm going to leave my condition blank for a moment so you can think about our condition. I want to print the numbers 1 to 1,000. 1 to 100, but only in multiples of 6. So I think our condition should be pretty much the same, right? Go 1 through 100. And that's it. What's going to change how much the loop occurs is the condition or the work inside of the body. So we'll say, well, num is less than 100. Actually, we should include 100 because I want it to be included potentially, even though it's not a multiple of 6, it could have been, and that's what I want to make sure we include. So what is our thing? Instead of just printing the number, we should ask ourselves, well, is it a multiple of 6? How do we ask the question? A conditional statement would be good. And so are we going to use an if, or an if-else, or an if-else if? We have to consider, well, what are the possibilities? What do we want to do? If it's a 6 or a multiple of 6, we print it. If it's not, we do nothing. So we only really need the if statement, right? It's a conditional print. We don't print every time. So we'll ask, if the number is a multiple of 6, how do we know something's a multiple of something? We do the modulus. If we get 0, then it's a multiple, right? Because if I say 8 mod 2, we get 0, because 2 goes into 8 4 times evenly. If I say 36 mod 6, we get 0, because 6 is a multiple of 36. If I say 42 mod 6, we get 0, because 6 times 7 is 42, right? It's a multiple of 42. So the idea is that we can do modulus by a number, and if it's 0, that means it's a multiple. So I said 6, so we'll say mod 6 is equal to 0. That is a Boolean condition. It's either true or it's false. And what does our body say? Well, only when this is the case do we print out our number. And then, of course, we do need our kind of update. Otherwise, if num didn't change, and I'm actually going to leave it like this now, and we'll see what's going to happen. I'm going to do it on purpose. I'm going to forget to increase num by some fashion. And here we go. I'm going to run it. And we'll see our first kind of experience with a loop. Notice the program's not over, but you don't see anything printing. So why is this happening? Num is 1. Is 1 less than 100? Yes. Is 1 mod 6 equal to 0? No. So we skip it and we come back. Is 1 less than 100? Yes. Is 1 a multiple of 6? No. So it's stuck on the number 1 forever, and this program will never, ever end. The way it's, and in fact, I'll show you my performance on my computer. We can actually see the CPU was working kind of hard, And if I look at my processes and I look at NetBeans, it's running at 14% of the CPU because it's not stopping. The program is still going. I'm going to kill it. I'm going to hit the red button to stop it, and watch the percentage drop because NetBeans will suddenly be doing less work. I'm going to hit stop, and bam, you see how it dropped basically to 2%. This is just the kind of the IDE itself, not any actual program. 58 seconds. It was never going to end. That could be a huge problem. An infinite loop is dangerous. So we have to make sure that if we write a condition, that the condition could potentially or eventually be false. Otherwise, we're in a bad situation. So whether or not we print it, that's the conditional part. But one way or the other, we should increase our number by 1. Why am I not adding 6 to just jump around? Because again, I said that the question, if we start at 1, then we can't add 6 because that would put us at 7, so we would never see the multiples. If we go up by 1 each time, yeah, we might be doing more work. We might be checking all 100 numbers, but this way at least I'm being strict about I'm going from 1 to 100. If I started at 6 and just added 6 each time, then we would get all the multiples and it might be a faster loop, but that's not so important to me. So here we go, let's run it now and see what happens. And there it is. 6, 12, 18, 24, 30, 36, and so on. Right? Those are all the multiples from 1 to 100 of 6. So I'm going to stop the video here. Our next video, we're going to do some more complex examples. We'll introduce strings, and we can see suddenly the functionalities that we've seen that were great with strings. Substring, index of, compare to. There's a lot of powerful tools, and now blended with conditions, conditional statements, blended with if statements. That's one power. And now we can repeatedly ask questions and repeatedly substring strings. Now we're at another level of complexity, and we can really make programs that are very dynamic. The problem, for example, that we saw briefly was if I have a string with multiple words in it, with white spaces between each word, before with index of, I could only kind of take the first word off and take the rest of it. Now we'll be able to repeatedly cut it in pieces and potentially, with no limit to how many words there are, separate every word in a sentence or separate every letter in a string or any kind of complex things like that. So we'll continue that in our next video.